Okay, welcome back to the last part of the lecture. We move on to motion of charged particles in a uniform electric field. Right, remember in a uniform electric field, the field strength is the same at all points, right? So the force on a charged particle is therefore a constant, right? So why? Because F equal to QE. So if the field strength is the same and the charge on the particle is the same, then the force must be the same. And therefore, generally, the charged particle moves with constant acceleration. Of course, we have to check whether this charged particle has any other force acting on it or not. Because we must realize it's F net equal ma, and it's only fair to put the electrical force here inside F net, assuming the free body diagram only has electrical force, right? The other alternative is that if, for example, we look at things like electron, right? Generally, does electron have weight? Answer is yes, right? Because the Earth still attracts the electron, but the weight is normally so small we can ignore it, okay? So that's why we ignore the weight of the electron when we use F net equal ma, right? So F electrical equal ma instead. So QE equal ma, right? And normally for parallel plate you realize that your E formula is given by modulus delta V over D, where D is the spacing between the plates, right? And this is equal to ma, and that's how normally you calculate acceleration. So there's the horizontal type of acceleration like this case. Why? Because the field is from positive to negative, remember? Alright, so it's this direction. So as the electron enters this field over here, it moves towards the right, It's actually being accelerated. Why? Because as it moves towards the right, the force on this electron is in this direction, right? Remember that field direction, right, which is this one, is the direction of the force on the positive charge. So the force on the negative charge must be opposite in direction to the electric field. Okay, so therefore this atom or this electron here is actually accelerating towards the right. Okay. We move on to projectile motion, right? So instead, if the plates are not or like that, right, it's like that, right? Then you have the field looking like that. And as it enters, and this beam of particles enters, let's assume that there's proton, electron, and neutron entering at different times. Neutron will pass straight through because there's no force, there's no electrical force. Why? Because the Q of the neutron is 0. So no electrical force means I pass straight through, right? Again, you can note here that I'm sort of assuming the neutron has no weight, right? Because it just passed straight through. Okay, if but by right, neutron obviously have weight but weight is negligible as compared to the speed of the neutron passing through, right? So that's why it looks vertical in this case, right? For electrons, you can see that it bends sharply upwards, and then for proton, it bends sharply downwards, right? Just from that alone, we can sort of guess that the electron actually experiences an outward force, but we can also derive that from the plates, right? Since the field is down, the force on electron must be up, right? Likewise, on a proton, the force must be down because proton is positively charged, right? Then the next question will be, why does the electron move so sharply upwards and the proton slowly move downwards? The answer lies in momentum, not momentum, sorry, inertia, right? Because if you look at the proton, right, the proton is much more massive than the electron, right? So if I look at this equation, which applies to this case as well vertically, you realize that the Q for proton and electron is the same because they have the same elementary charge. Delta V over D is the same because it's in the same plates, right? So this is the electric field strength, right? The only difference is proton is much more massive than electron. So vertically, right, given the same force, right, the acceleration for the proton must be a lot less because the mass of the proton is a lot higher. So that's why you see the bending of the proton is a lot less pronounced than the electron. Okay? Right. Uh, yeah, so we talk about this. For charged particle, very small mass, generally we can ignore the gravitational force, right? Generally speaking. But if the electric force is too weak, then you have to be careful. But generally, I think you can just ignore, unless there's something in equation to suggest otherwise, right? In both cases, under electric force, they will accelerate, alright? And this equation we already derived on top. I'm not going to say again. You can see this equation is exactly the same as this one. Right, so if you resort with A as the subject, you get this one. Okay, quickly do 19. Pause pause and do before you come back. Right, we're back from the pause. Right, two electrons are separated by 1 meter. What is the ratio of electric force on one electron and gravitational force on electron due to the other electron? So this is quite a simple question. You just substitute the equation. 1/4 pi epsilon naught QQ, where is the electron charge of 1.6 times 10 to the power minus 19, right? Over R squared, R is 1. So you can just substitute R and the R will disappear, right? Then divide by the gravitational force, right? Gm square, you can substitute the mass of electron inside here. And again, R is 1, so you just disappear, right? And you get this one, you press calculator, you should get this, right? So you can see the ratio of the electric force to the gravitational force is 4.2 times 10 to the power of 42. 10 to the power of 42 is just absurdly high, all right? So it's almost impossible for the gravitational force, actually in this type of case, electron, it's not possible for gravitational force to be anywhere close to the electric force, all right? So that's why we can ignore the gravitational force, generally speaking, right? But this electron, okay? Let's move on to the next question. All right, do try and pause and do this question. Okay, we're back from the pause. All right, so there's an electric field strength. This one should be multiplied, sorry. Oh, goodness. Okay, I'll correct this later. All right, this is a multiply sign here. All right, so the velocity of electron is this. This one's also a multiply sign, sorry. Right, again, I'll correct this later. All right, neglecting gravitational effects. Determine the distance it deviates toward the positive charge plate and the speed just as it leaves the electric field. So this type of question is like combining kinematics, dynamics, and electric fields. So we call this symbiotic questions. You should not be surprised that at A level, right, you will come across questions like that. Right? So what I want to do here is I want to apply my kinematics, right? And what I should probably think about is my suvat, right? So vertically speaking, right, I want to find Sy, or I don't know Sy. Uy, I know is 0 because initially I only have horizontal. So vertical velocity is 0. Vy I don't know, Ay I don't know, right? What do I actually know? Acceleration in x direction is 0, right? So in this direction is actually constant speed, right? So this u, right, in the x direction will not change, right? So ux is this amount, vx is this amount because again no acceleration, right? Sx is 5 cm, right? So change to meters, right? So if I want to find distance, it deviates towards the positive charge plate. So I'll try and find sy, right? I'm trying to find sy. So one way to find Sy is to find time first. So I use the horizontal aspect to find time, right? So this is actually distance equals speed times time, right? You will find that the time it travels within the plate to be this, right? So knowing time now, I can try to use sub this time into the vertical aspect, right? So vertical electric force can be calculated by 1.6 times 10 to the power minus 19. Okay, apologies for this again. This should be a times. I'll fix it later, right? Multiply by the electric field strength, which is given by 3.5 times 10 to the power 4, right? Given here. And this will be the force, right? And you can calculate acceleration by force divided by mass of electron, right? And that will give you the acceleration vertically, right? Then you can use your S equal ut plus half at square to find Sy. Can? Right? For B, speed as it just leaves the electric field, right? So I want to find Vy now. Right, to find Vy, you can again use your kinematics. I don't think this is too difficult. Then, of course, this is only the vertical aspect, as you remember from your kinematics. Hopefully, this vertical aspect. Your horizontal is the same as what is given earlier, right? And then you calculate resultant to be this one, right? Which is this value over here. Can? All right, we'll move on to, I think, now appendix, right? Yeah, definitions list. All right, this definition list is basically to define most of the important things in this chapter, but you will see that I only need to memorize on two things, right? I was contemplating whether I should tell you this one no need to memorize according to LO lah, but very hard to say. Sometimes A level also test things that they never say must memorize. So whether you want to memorize this type of thing or not, you decide, all right? But this type of thing need to memorize, okay? Can? And this one also need to memorize because this one is in L, right? The rest I leave you to your discretion, okay? Right, these are the analogous ideas between electric field and gravitational field. Right, again, it's a good read through, right, as to the similarities and differences. Right, I'll just go through one last formula that I think most people Actually, I think most of you know lah, right? But I'll just go through it one more time, right? Change in gravitational potential energy is equal to mass times change in gravitational potential, right? This for the gravitational side. For electric side, change in electric potential energy is charge times change in potential, right? Very similar. Again, I just remind you, mass got no sign lah, so this one is always positive. Q, try to sub with the sign inside, right? Because it's a scalar. Right. With that, I think I can end the lecture. Yeah, annexes you read. I think it's good for you to read through because there are a lot of interesting information inside for you to have a more holistic understanding of the chapter. Right. But strictly speaking, a lot of these things are not in the LO lah, so you don't really need to know. Right. Except maybe B lah. But B is already in the notes in front lah. So it's just a mind map for the formulas that we are using. Then all these derivation stuff not in your syllabus, but good to know again. There are some interesting things that are inside for you to read lah, right? So optional reading, right, and annexes, right? With that, I end the lecture.